Hi friends, welcome to my channel. Nowadays we are discussing topics from higher secondary mathematics. Today's topic is composition of functions and inverse of a function. Let me start with the definition. Consider two functions f and g. F is a function from the set A to the set B, where g is a function from the set B to the set C. Then the composition of these two functions is denoted by g of f, and E is a function from A to directly to C. It is given as g of fx is equal to g within bracket fx. That means that the function fx is within the function g. For all x belongs to A is the domain of the composite function. We can have a diagrammatic representation of this. Consider three sets A, B and C. Now the functions f and g are defined in this way. Then the composite is denoted by g of f is a function directly from the set A to the set C. So it is written like this. You can see by considering an element x from the set A. Since f is a function and x is in the domain of f, that means x has an image under the function f, and that can be written as fx. And since fx is in the set B, which is the domain of the function z, therefore fx must have an image under the function z, which is written like this, z of fx. We have seen that x has been mapped onto the element z of fx in two steps under the functions f and g, which can be combined into a single function such that x has been mapped onto z of fx directly under the function z of f, and then that z of f is called the composition of the two functions. The process is somewhat similar to the following game. Consider a table containing 4 balls on it, which are marked with numbers 1, 2, 3 and 4. Consider 2 more tables having empty boxes on it, which are also numbered like this. Let there be a person standing between the two tables A and B, whose name is suppose F, who transfers the balls from the table A into the boxes on the table B. And let there be one more person standing between the two tables B and C, who in turn transfers the balls from the boxes of B into the boxes of C, like this. Let F transfers the balls in this way into the boxes, and then the person Z does it in this way, and the third person appears, who observes the rules by which the two persons are transferring the balls. And what he does, he transfers the balls directly from the table A into the boxes on the table C. He actually combines the rules of the two persons into a single process, and this is similar to the composition of the two functions z and f. In the first two processes, the balls have been transferred like this into the third table from the first table. Now the third person does what? He sees the rule followed by the two earlier persons and transforms these 4 balls into the respective boxes like this. Here you can see, if f be a function from the set A to the set B and Z be a function from the set B to the set C, then their composition called Z of f is a function from the set A directly to the set C. It is like this. You can see in the diagram, domain of the composite function is the domain of the function f, that is the set A, and codomain of the composite function is the domain of the function Z. It will be in this way. We can consider making a composition of three functions like this. Consider three functions f, z and h in this way. Here we can take four sets like this, and the functions f, z and h are defined on the sets like this. Then consider an element x from the very first set. Under the function f, this x must have an image which can be written as fx, and the image of fx under the function z can also be written like this, g of fx. And for the third one, since c is the domain of the function h, therefore z of fx, that will be an element actually, it will have a value. So image of this value under the function h is h of z of fx. That's how we can combine these three functions into a single function, composite function like this, directly from the set A to the set D. That means in this way the composite function will map the element x onto its image h of z of fx directly. So that's how we can combine two or more functions. Consider the function f from the set 2, 3, 4, 5 into the set 3, 4, 5, 9, and one more function z defined in this way, and also the values of the functions f and z are given in this way. We need to find the composite function, that is z of f. Let me draw the functions in this way. These are the three sets where the functions f and z are defined in this way. Then z of f is the function, composite function defined from the very first set to the last set, where we can find the values of g of f in this way. See, under f the images of the elements of the first set are like this, and the images of the second set under the function g are like this. If we follow the arrows, then we can find the images of the elements of the first set in the third set under the function g of f in this way. G of f2 is equal to 7 because 2 goes to 7 there. G of f3 is equal to 7, 3 goes to 7. In this way the other two values like this. We can consider one more function f1, 3, 4 from 1, 3, 4 to the set 1, 2, 5, and similarly z is a function defined in this way, where f and g are given in this way. F and g are given. We need to find the composition of z of f. Here also we can consider as three sets in this way. F and g are functions defined. So z of f can be found as earlier. You can see the arrows and find the values of z of f. That is z of f1 equal to 3. G of f3 is equal to 1, like this. Hence g of f, the function g of f can be in this way, 1, 3, 3, 1, 4, 3. Let me proceed to another example. Let us consider two functions. One is defined as fx equal to sin x, and the other is gx equal to x square. Now g of fx is equal to z within bracket fx is written, it means that the function fx is within the function g. Okay, in this way you have to write, and if we put the value of fx there, fx is sin x, and follow the rule of gx. And what is gx? Gx is x square, means we have to replace x by sin x. We get it like this: g of sin x will be sin square x. Now the case is that what is the domain of this function f, g of f? We know that the domain of the function f will be the domain of the composite function g of f. What is the domain of the function f? Fx is sin x, therefore sin x will have the domain as the set of all real numbers, means sin x is defined for all real numbers. Therefore the domain of the composite function g of f will also be the set of real numbers. And what will be the range? The range is always the range of the function g. Now g is the function gx equal to x square. We know that the square function x square has a range of the set of all non-negative real numbers. We know that the squared quantity of square of a real number never becomes a negative quantity. Therefore range of the composite function g of f is the set of all non-negative real numbers. Again, let us find what is f of gx. By definition, f of gx will be like this. Put the value of gx there. What is gx? Gx is x square. Therefore we get f of x square. But we know that fx is equal to sin x. Therefore f of x square is equal to sin of x square. Now in this case we can see that in general g of f and f of g, these two composite functions are not equal. The domain of g here, in this case the domain of g is the set of real numbers, and this will be the domain of f of g. Similarly, the range of the function f is nothing but the closed interval -1 + 1. Why? Because fx is equal to sin x, and we know that the values of sin x lie between -1 and +1, including -1 and +1. So the range of f means the range of sin x is the interval, closed interval -1 + 1, and which will be the range of this composite function f of g. These are the differences of g of f and f of g. Whatever we have said is written there. Okay, let me proceed with one more example. Here two functions are considered as fx equal to 8x cube and gx equal to cube root of x. We need to find g of f and f of g. So here both the functions are such that their domain and codomain are same, that is the set of real numbers. Now g of fx is equal to z fx. Put the value of fx. Fx is given as 8x cube. Now what is gx? Gx is equal to cube root of x. That means whatever be inside the bracket, the cube root of that value. Now here inside the bracket it is 8x cube, so that means g of 8x cube will be equal to cube root of 8x cube, and that gives us the value as twice x. So that means g of fx is equal to twice x. Let me find the other value, that is f of gx. To find f of gx, we put the value of gx here. What is gx? Gx is given as cube root of x. Now follow the definition of fx. Since fx is equal to 8x, therefore whatever be inside the bracket it is there x to the power 1 by 3. So we have to multiply it by 8 and make the cube of it, that is 8 into, and in that way it gives us the result as 8x. That means g of f and f of g are not equal in this case. Here you can see, by taking one particular example, consider the element 2. 2 is an element from the domain. Suppose, what is the value of f2? f2 is equal to 8 into 2 cube. Follow the rule of fx. It is 8x cube. So 8 into 2 cube, and that will give us the value as 64. And here also, the image of 64 under the function g is equal to cube root of 64. Cube root of 64 will become 4. That means after 2 steps, the image of 2 is obtained as 4. We have to do 2 calculations here. The image of 2 has become 4 after 2 steps. But if you consider the combination of these two functions, that is the composite, it is written as g of f2, and we have already found that g of f2 as 2 into 2. The rule is g of fx equal to twice x. Already it is found in the other slide. Okay, and that gives us equal to 4. That means the image of 2 can be found directly in one step. That is the benefit of the composite function. There is a note here. You can see the composition of 2 or more functions reduces the calculations of all the functions into a single operation. In fact, any number of functions can be made into a single composite function, which reduces the steps of calculations. Of course, there are some conditions involved in this process. Let me discuss some other problems like this. Consider a function fx equal to 4x plus 3 by 6x minus 4, and this is a rational function. So we have to show that composite of f with itself gives the image of x as x. That means f of fx is equal to x. It is nothing but the identity function. So let us show it. What is f of fx? It is like this. Put the value of fx. Fx is given as 4x plus 3 by 6x minus 4. Now again you have to consider the bracketed quantity as a single value and operate the function again. What is the rule of fx? You have to multiply the value inside the bracket by 4 plus 3, and that is in the numerator, and divide it by multiplying the same value by 6 minus 4. So if we do the same calculation, we get it like this. You can see the calculation simplification. After simplification, we get it like this. The end is the value x. That means under the composite function f of f, the image of x is x, and that is what is to be shown. Then comes the concept of invertible function. You can see one thing here. See the diagram. So let f be a function from the set A to the set B. In this way, it is defined in this way. Then the inverse of this function f is a function from the set B to A. It is like this, from B to A, such that the elements are related like this. If the image of A under the function f is x, then the image of x under the function f inverse is A, and this is what is the inverse, concept of inverse. What is the definition? You can see it here. Consider a function f from x to y. So it is defined to be invertible if there exists one more function from the set y to the set x. From the set y, here it is written as z from y to x, such that z of f is equal to ix and f of z is equal to iy. Here I means the identity function and the suffix x means that identity function is from the set x to x, and iy means the identity function from the set y to y. That means whatever be the order of the composite function, it will give us the identity function if f and z are inverses of each other. Now the inverse of f is denoted by f inverse, like that we have written there. Let us consider a function f from the set n of natural numbers to the set y, defined in this way: fx equal to 4x plus 3, where y is the set such that y's are all natural numbers, y equals to 4x plus 3 for some x belongs to n, for some natural number x. Show that f is invertible and also find the inverse of f. So for that we consider an element y from the codomain y, codomain set y. So now by the definition of the elements of y, the set y, we have an x in the domain n, means for every y we will have a natural number x such that y equals to 4x plus 3. That means y has been expressed as a function of x here. We can reverse the order in this way. We can find the value of x in this way, x as y minus 3 by 4. X is expressed here as a function of y. Now define a function z from the set y to the set n by zy equal to y minus 3 by 4. Y minus 3 by 4 is the value just we have obtained for the value of x. Now what is z of fx? Z of fx, you try to find it like this. Put the value of fx. Fx is given as 4x plus 3. Now 4x plus 3 is within the function z, and the definition of z is there above in the first line. Gy is equal to y minus 3 by 4. That means z of 4x plus 3 must be equal to 4x plus 3 minus 3 divided by 4, and upon calculation it gives us as x. And what is z of fx? Now it is z of fx, already we have found. What is f of gx? F of gx can also be found as earlier. Put the value of gx as x minus 3 by 4. It is defined in the other slide. Now f of x is 4x plus 3. Therefore x minus 3 by 4 is within the bracket, you can see, within the function f. Therefore if we follow the rule of f, we get it like this: 4 times of x minus 3 by 4 plus 3, and upon calculation it also gives us the value x. Thus f of gx is equal to x. And for both the cases, z of f and f of z are coming out to be the identity functions. Hence g must be the inverse of f. From this we can conclude that one function is the inverse of the other if the composite is the identity function, in whatever order you take it. You remember this one. Important notes are there. The necessary and sufficient condition for a function to possess an inverse is that it is bijective, or 1 1 and on 2. Necessary and sufficient means if a function is bijective, then it will be invertible, and if the function is invertible, it must be bijective. The second one is, to show that a function f from a to b is invertible, you can show that there exists a function g from b to a, such that, I told you this one earlier, g of f is equal to the identity function, and f of g is also the identity function. Let me show you one more method of showing a function to be invertible and also finding the inverse of that function. Consider a function f from the set R plus, that is the set of non-negative real numbers, to the set of all real numbers right from 4 up to infinity, defined as fx equal to x square plus 4. So we need to show that this function is invertible. So for this one, what we use the concept of bijective function. A bijective function is invertible. So let me show you that this function is bijective. Let us consider two elements from the domain of the function. Those are x1, x2, such that their images are same. That is, fx1 is equal to fx2, and that will mean that x1 square plus 4 is equal to x2 square plus 4 by the definition of fx. It is given above there. Okay, now if you solve it, 4's will cancel. It will look like this. Now x1 square minus x2 square will become 0, and upon factorization and solving, we will get it like this. The values of x1 and x2 are equal, because x1 minus x2 will become 0 here. See here, the other case, x1 plus x2 equal to 0 is not considered, because that will give us x1 equal to minus x2. But we know that x1 and x2 are all positive real numbers, means non-negative real numbers, actually non-negative real numbers whose sum cannot be equal to 0. Thus we get that f is a 1 1 function. For the second part, let us consider an element y from the codomain of the function. Yes, from the codomain, that is 4 to infinity, such that y is equal to fx. We let it like this. So upon putting the value of fx, we get it like this: y equals to x square plus 4. Now, as we have done earlier in earlier problems, so we try to express x as a function of y, just like this, and that will give us x equal to root over y minus 4. That negative sign is not considered, as again I told you x is a non-negative quantity, therefore only positive square root will be considered here. Now we can see for all y's from the codomain, y's are also positive numbers. It is right from 4 to infinity. You can see if we put 1 by 1 or any real number from the codomain, then the value of x will be a real number, because y starts from 4 itself. And hence we see that for every element y of the codomain, there exists an x in the domain, such that fx is equal to y. Means every element of the codomain will have a pre-image in the domain, and that shows that the function is onto. Since it is already 1 1, it is now onto, and consequently we can say that the function f is a bijective function, and we know that a bijective function is always invertible, so hence we can write it as invertible. And for the inverse of this function, we can define a function like this: f inverse. It is from the codomain of the function f, that is 4 infinity, to the domain, that is R plus, and the definition will be like this, defined as f inverse y equal to root over y minus x, which we have found in the other slide as the value of x. That's how we get the value of the inverse function. Now let me proceed to the next concept, that is the uniqueness of the inverse. Let us consider a function f from the set x to y to be invertible, and let us consider z1 and z2 be two inverses of f, two inverses of f. Now we try to show that these two inverses are actually the same one. There cannot be two inverses, two different inverses of a single invertible function. Now since f is invertible, we know that f is a 1-1 function. F is 1-1 function. Now z1 and z2 are inverses of f, therefore their composition with f must give you the identity function in this way. F of z1 must be equal to iy, f of z2 must be equal to iy again. And since the right hand sides of these two equations are same, therefore the left hand sides must also be same. That means for all y from the codomain of f, f of z1 is equal to f of z2, and by definition we can write it in this way: f of z1 y is equal to f of z2 y. And now since f is an 1-1 function, and we know that in a 1-1 function, just like if fx1 equal to fx2, then x1 must be equal to x2. So here it is of that form: f of z1y is equal to f of z2y, and f is 1-1, therefore z1y must be equal to z2y. This follows from the concept of 1-1 function, and this shows that z1 and z2 are actually the same function, and hence the inverse of an invertible function is always unique. There cannot be more than one inverses. Well friends, these are some topics, some concepts of composite functions and inverse of a function. I hope you like this video. If you have liked it, please click the like button and subscribe to my channel. Thanks for watching.